So welcome to the NPA Seminar. We're happy to have Clarke Hardy today from Stanford. So Clarke did his undergrad and master's in Canada, working on the NewsG and Pico dark matter searches. And then moved to Stanford for his PhD work. I guess initially started on LZ and then coming to the other xenon detector at Stanford, working on searching for neutrinos double beta decay with nEXO, Georgia Gratis group, and then also now working on searching for new micron-scale interactions with levitated optomechanical systems. So won a number of awards, including an NSERC doctoral fellowship supporting your PhD work. And we're very happy to have him, and in fact successfully defended a week ago as the topics we'll be talking about here. Yeah.
Thank you for the introduction and for having me here and everything. I'll address the title first. The fact that this is my defense talk is, I think, helpful context because these are in fact not these are not related topics. These are two distinct topics. So I'm going to give two talks in one. In the first part of the talk, I'll talk about Majorana neutrinos. I'll talk about why this is something we're interested in, and to essentially complete the standard model with neutrino masses. And specifically, I'll talk about how we use neutrinoless double beta decay and nEXO to try and answer that question. In particular, my work on nEXO was involved in designing a calibration scheme and also a xenon purifier. Okay, so that's the first part of the talk. The second part, I'm going to switch gears completely and talk about micron-scale interactions. So I'll first discuss gravity at the micron scale and some experimental efforts to understand that. And then I'll talk about how we use optically levitated microspheres to try and search for interactions at that length scale. And I'll finish by discussing some background reduction strategies for that search. Okay, so for part one, the question that we're trying to answer with nEXO is how do neutrinos get a mass? It's often easier when you're confronted with a difficult question like this to ask an easier question first. And this one happens to be an easier question because we know the answer to it already. So how do electrons get a mass? And this is understood in the standard model. So if we take a really kind of minimal version of the standard model here, we have left and right-handed electron fields. We have the Higgs field, which before electroweak symmetry breaking, it's just sitting at 0. And the result of that, the fact that the Higgs field is at 0 means that there's no interaction between the left and right-handed fields. The electrons are massless, and that's kind of the end of the story. Until electroweak symmetry breaking. At this point, the Higgs takes on its vacuum expectation value. The Higgs is now at non-zero. It can interact. It can participate in these interactions. And specifically, it can interact with the left and right-handed electron fields by this interaction that I'm showing here, which gives rise to a Dirac mass. And so this is why electrons are massive after electroweak symmetry breaking in the standard model. So the mass is proportional to this vacuum expectation value of the Higgs, and it's also proportional to the coupling strength, which I've called Y sub E here. So this is the answer to the easy question. Now the hard question: how does this work for neutrinos? Why can we not apply this to neutrinos? The problem is that experimentally, we've only ever observed left-handed neutrinos. And as I showed, you need both the left and right-handed fields in order to get this Dirac mass. If we try the same thing with neutrinos, we find that even after electroweak symmetry breaking in the minimal standard model, which only has the left-handed neutrinos, there's no gauge invariant way for the left-handed neutrinos to interact with the Higgs and give rise to a mass term. So the reason this is a problem is, of course, because we know neutrinos have mass from neutrino oscillations. So what this means is that if we produce neutrinos in one flavor state, after they've propagated some distance, depending on their energy, there will be some non-zero probability for them to be measured in a different flavor state. This can only happen if neutrinos are massive. And so by doing measurements of these neutrino oscillations and solar neutrinos and atmospheric neutrinos and reactors, we can put together this paradigm in which we have the three flavor states here, we have three mass states, and we can start to narrow down on some of these oscillation parameters that allow us to fully describe the flavor and mass states and how to interchange between those two. And so what we know now is that there are two remaining ordering scenarios. We know that M1 is lighter than M2, but we don't know whether these two are lighter than M3 or heavier than M3. So that gives us two ordering scenarios. We also know from this that neutrinos are much less massive than any other fermion. So you just plot the fermion masses here. You see there's about a 6 order of magnitude gap between the neutrino masses where they're constrained to be by experiment and the next lightest fermion mass. And so that in itself is an interesting question. If neutrinos get their mass in the same way, then why does the coupling have to be so much smaller? And so we know that neutrinos have mass. We have to extend the standard model to account for this. How do we do that? The obvious way is just to add right-handed neutrinos. This is how the other fermions get masses. It makes sense that this is how neutrinos should get a mass as well. So you add the right-handed neutrinos, and indeed you get this Dirac mass term as before. But you get another thing. When you've added right-handed neutrinos to the standard model, you've changed the particle content, and so you should think about the implications of that for the theory. And one thing that you find is that unlike with the left-handed only case, the right-handed neutrinos are allowed to interact with themselves. This is totally consistent with the symmetries of the theory, and that gives you what we call Majorana mass. And so this is kind of in the spirit of Murray Gell-Mann's totalitarian principle, which says everything not forbidden is compulsory. This interaction is not forbidden by the standard model. It's allowed, and so in fact we expect, loosely speaking, we expect to see this. Of course, there are reasons why it might not exist, but just given kind of this basic picture, this is definitely something that we should look for. So they can't have the only Dirac mass. There's no reason why that Majorana mass can't be set to 0, but that would be strange because the coupling required to set the Dirac mass at the measured scale has to be really tiny. However, if we include both mass terms, so we have the Dirac masses that I showed first, and then also the Majorana mass. If you actually work out the physical mass eigenstates, you find that the neutrino masses become naturally small at roughly the scale that we would expect, or that is consistent with our measurements of the neutrino mass from these oscillations. And so what this also gives you is the fact that you can start with a neutrino, and via this insertion of these 3 different mass states, you can go from a neutrino to an antineutrino. And so this is why people will sometimes say that neutrinos are their own antiparticles if they're Majorana particles, because of this allowed process that flips between one and the other. Okay, so how do we test for Majorana neutrinos? I want to start off by saying how we don't do this, because I think it's helpful to kind of frame the question. If you hear that neutrinos may be their own antiparticles, one obvious way to do it, to do this test would be to create a source of antineutrinos, say in a nuclear reactor where you get a high flux of neutrinos or antineutrinos from beta decays. And then you put an inverse beta decay target nearby, and you look for an interaction that can only occur with neutrinos rather than antineutrinos. And so you look for this mass insertion that takes you from the neutrino, from the antineutrino to the neutrino, and then you've shown that neutrinos are Majorana. So now my question to the audience is, why does this not work? Flux, yeah. So I mean, flux is the ultimate problem, yeah. And specifically, the reason is that this process is suppressed by the neutrino mass divided by the neutrino energy squared. So the neutrino masses are very small. The energy from beta decays is like MeV scale. So this is a really, really strongly suppressed process. And it's suppressed by about 10 to the 14, depending on what specific numbers you put in there. And so the result is that this is just not something you can observe. So really what you need to do is you need to get a much higher rate of this process in order for it to actually be observed. And one way to do that is to look in an atomic nucleus where this process can happen in a way that we can hopefully measure at some point. And so specifically what I'm talking about is double beta decay. So I'm going to start out by talking about 2 neutrino double beta decay. This is essentially 2 simultaneous beta decays that can happen. That's an energetically favorable process in certain even nuclei. It's a really rare process with a typical half-life of around 10 to the 20 years, but it has been observed in a number of different isotopes. The result of this is that you have electrons emitted, you have antineutrinos emitted, the antineutrinos escape, the electrons deposit their energy in your detector, and as a result of this energy sharing, you get this continuous spectrum of electron energies. Whereas neutrinoless double beta decay, on the other hand, we'll include this mass insertion that in some sense is like the annihilation of the neutrinos in this diagram, and the result then is that the electrons take all the energy. And so if you want to search for this process, you look at the Q value of the decay for this little spike that's indicating a surplus of these events. So this would have really significant implications for understanding of physics in a lot of different ways. So for one, it could suggest that neutrinos are Majorana fermions, which is of course the way that I introduced this topic. This will tell us about neutrino mass generation. It would provide direct evidence of the non-conservation of lepton number, because in producing 2 electrons, you're violating lepton number by 2 units. It could hint at a possible mechanism to explain the matter-antimatter asymmetry that we observe in the universe. And in addition, via the seesaw mechanism, it would provide an explanation for the fact that the neutrino mass scale, the absolute mass scale, is so much smaller for neutrinos than for all other fermions. So I hope I've convinced you that this is worth looking for. I know I don't need to convince many of you who already work on nEXO. But anyway, yeah, I'm going to talk about the nEXO experiment. So nEXO uses a single-phase liquid xenon time projection chamber to search for this process. And what that means is that we're using liquid xenon to detect the depositions of energy by the scintillation light they produce, which I'm showing in magenta here, and the ionized charge, which I'm showing in blue. And so the way that we do this in nEXO is we have the barrel of our detector tiled with silicon photomultipliers that collect the light. The charge is drifted through a uniform electric field to a charge an anode plane that's tiled with a bunch of charge-sensitive detectors. The combination of these things gives us the 3-dimensional position of these events. So we get X and Y based on the location of the charge arriving on the anode plane with about 3 millimeter resolution. And the Z we get from the fact that the light signals are prompt and the charge signals drift slowly comparatively through the liquid xenon. And so that allows us to infer from the drift time the Z location. And then using both light and charge, we can reconstruct the energy of these events. And in fact, we can get better resolution on the total energy by summing light and charge than we could get by using any one alone. So this is kind of what we're doing in nEXO. nEXO is a planned experiment that'll use 5 tons of xenon enriched to 90% in xenon 136, which is an isotope which undergoes double beta decay. It's a successor to the X200 experiment, which used this technology on a smaller scale. It'll be located in Snow Lab near Sudbury, Ontario. And we're hoping, I mean, this is kind of up in the air at the moment, we're hoping for data collection to begin at some point in the 2030s. And of course, nEXO is an international collaboration with many participating institutions, including Yale. We have around 200 scientists total from many different countries. So nEXO, in addition to using energy, as I mentioned, is using a couple other parameters as well to enhance the sensitivity to this process. So energy, I've already addressed, but just to reiterate this, we're looking for events that occur at the Q value, which in our case is around 2.5 MeV. So anything near the Q value is signal-like, anything further away from the Q value is background-like. In order to do this search well, we need to have good energy resolution. So we need to be able to calibrate the response of our detector to depositions of energy in both the charge and light channels, and ideally to better than 1%. And then in addition to that, it really helps to have low backgrounds near the Q value so that the only thing we're getting there are signal events. And so this kind of frames the parts that I'm going to be talking about, this calibration and identifying and mitigating potential background sources near the Q value. So in addition to energy, we use standoff, which is what we call the distance to the nearest detector surface. We use this because backgrounds that are produced in detector surfaces are strongly attenuated by the liquid xenon itself. So the background rates get much smaller as you go further from the walls of the detector. So this gives us an additional axis in which we can get separation between signal and background. The final one is the event topology. So the neutrinoless double beta decay events will create localized energy depositions in a single site, whereas gamma backgrounds can scatter multiple times. And so we use a deep neural net to do this discrimination between signal and background in topology. And when we put these all together, I'm just showing some simulated data for nEXO. So we get good signal background discrimination in each of these panels individually. And when we put these together, this gives us better sensitivity than using any one. So our sensitivity, the sensitivity that I'm going to talk about, or that we ultimately care about, is our sensitivity to the effective Majorana mass. But really what we're doing is we're measuring a half-life. So we're measuring a number of counts over a period of time. To get from the half-life to the effective Majorana mass, we use this equation, which includes the nuclear matrix element. This is a quantity that has a really large uncertainty. It has to be calculated. It's not well known at this point. And so this is going to be the largest source of uncertainty in our projections of our sensitivity. It's typical to show our sensitivity on these types of plots where we're plotting for each ordering scenario the lightest mass state on the x-axis, and then the y-axis is this effective Majorana mass that we're interested in. And so the contours in black with this yellow filled region here are denoting the areas of this parameter space that are allowed by oscillation data. So if we make a discovery, it'll be somewhere in these regions. And then the blue band is showing nEXO sensitivity considering all different calculations of this nuclear matrix element, which gives us some width here. This I think kind of hides some information, which is that we actually know from measurements of existing oscillation parameters kind of how to better understand where the Majorana mass is likely to live in this plot. So we make some common sense assumptions. We choose some common sense priors, and you can do a Markov chain Monte Carlo and essentially profile the posterior distribution of this parameter. And what you find, now just considering one nuclear matrix element, is that actually, even though if you just looked at this in the naive picture on the last slide, you'd say that we have really good sensitivity to the inverted ordering, but maybe not so good sensitivity to the normal ordering. Here you can see that actually we're covering a lot of the interesting parameter space in the normal ordering as well, because from our best fit neutrino oscillation parameters, we know that this is an interesting region of the parameter space.
There's a uniform linear prior on mass.
Log uniform on mass, yeah. Yeah, log uniform on mass, angles uniform 0 to 2 pi. Okay, so with that, I'm going to talk about my work on developing a calibration scheme. So addressing this part of achieving our energy resolution goal. And so in particular, I'm going to talk about using an internal xenon 127 source. So just to introduce this topic, we need to do this because our collection efficiency for both light and charge varies pretty significantly across the TPC. So what I'm showing here is the three-dimensional light map or the light collection efficiency. And so we need to correct this to measure our the light contribution to the energy with adequate resolution. And then in addition to that, we have a significant variation in our charge collection efficiency as well. Really, this only depends on the Z position because as charges drift through the TPC up to the anode, depending on the concentration of impurities in the xenon, some fraction will be captured and that will result in reduced charge collection at the anode. And so I'm showing that for 3 different impurity concentrations here. We report this in terms of the electron lifetime. So this is related to the impurity concentration. So as you can see from this plot, the higher electron lifetime gives us worse attenuation of our charge signal as a function of Z. And so in order to optimize this for nEXO, we want to ensure both that the impurity concentration is as low as possible, and also we want to correct the remaining fall off that we get with the electron lifetime. So in terms of how we actually do this, there are a few different ways that we can deploy calibration sources in nEXO. Possibly the simplest way is just to use an external gamma source, which happens to be comparatively easy to deploy because we can just put the source in a source tube that's positioned near the outside of the TPC. The advantage to this is that we can choose from a wide range of calibration sources and get whatever energies we want to cover the full range of interest. And there's also no risk of introducing backgrounds because we're not breaching the liquid xenon volume. The problem with this is that because there's such strong attenuation of gammas in the liquid xenon, it's really hard to get events into the center of the TPC. And so to do this, we kind of have to pause data collection. We have to wait until we get enough events throughout the TPC, and this means sacrificing lifetime. The alternative, or one alternative, is to use internal alpha sources, which happen to have excellent energy resolution. And the advantage that they have over the external sources is that by mixing the source throughout the xenon, we get a uniform illumination of the detector volume. So we get just as many events in the center as we do towards the edges. Again, though, this requires sacrificing a lifetime because we're introducing a potential source of backgrounds. And so that brings me to the specific internal source that I worked on, which is using xenon 127. So this is an electron capture decay to excited states of iodine 127 with a half-life of 36 days. The idea behind using this source is that we would maintain an activity of about 1 becquerel during the calibration period. The activity is low enough that we actually don't need to worry about losing lifetime at all. We can do this during data collection. So I'm showing a level scheme here. When you actually look at how that at the resulting charge and light signals, you get something in the plot on the upper right here with these 4 main energies, which when you project onto the charge and light axes result in 2 broad peaks with an intrinsic peak width of about 10%. The lower energy peak is at around 200 keV, which is roughly nEXO's threshold. So we're going to use only the higher energy peak, which is around 400 keV. That also happens to be much below the Q value of 2.5 MeV. So it's not interfering at all with our actual physics measurement, which is why we can do this in situ. So this is kind of my outline of what the development of a calibration source might look like. So you want to show, first of all, that you can produce the source, and then that you can actually deploy the source. And in deploying the source, of course, we want to do this in a test TPC to the extent that that's possible. Where it's not possible, we can deploy it in simulation of the full-scale detector. Both of these will give us some calibration data that we can then fit, and then we can reconstruct the light map and the electron lifetime and compare our reconstructed parameters to the truth values that went into the simulation and quantify how well we've done. So focusing on the source production step first, xenon 127 is a synthetic isotope of xenon, which means we need to produce it. And in particular, the way we do that is we produce it via neutron capture on xenon 126, which has some small natural abundance. So we did this by irradiating a sample cylinder containing roughly 70 grams of xenon at a nuclear reactor facility. What we could then do after irradiating the cylinder is remove the xenon from the cylinder and assay the cylinder itself. And then just based on the activation of radioisotopes in the cylinder, we can then calibrate the neutron flux that the cylinder was exposed to. This in turn lets us predict the type of activity that we should see in the xenon itself. And if you look at that, you can see that we have a number of different radioisotopes produced as a result of this process, but that if you wait for about 100 days after the irradiation, you find that almost everything has died away except for the xenon 127. And so the nice thing about this is that we're not introducing all sorts of other backgrounds in, provided we wait for this cool-off period before doing the calibration. So we first deployed this source that we produced in a test TPC on Stanford campus. So just to kind of give the quick overview of this test TPC, we have a CIFM array at the bottom, which we use for triggering. The drift length is about 14 centimeters, and at the top we have a prototype charge tile, which allows us to measure the charge energy. And so we injected the activated xenon into this test TPC, and we're able to see from the increasing trigger rate as we did so that we're actually getting the xenon 127 decays in the TPC. And then if you just look at our data, this is what it looks like. So here I'm showing the charge detected on the y-axis and the drift time, which is a proxy for the z position on the x-axis. If you squint at this, you might be able to see 2 broad peaks. It's much easier to bin these by drift time and just look at histograms, in which it's much easier to extract the 2 individual peaks. And if we do a fit to these, we can fit them plus some background term. We do this for all different bins in the drift time, and that allows us to extract the charge as a function of the drift time, which we can then fit our electron lifetime model to. And so we showed that we're able to use this to do electron lifetime measurements in kind of a small scale prototype for nEXO. Okay, so that's the electron lifetime piece. Now I'm going to talk about the light map. So this was done completely in simulation because we don't have a detector with good enough light coverage to do this in an actual TPC. So I did this by producing simulated data sets with nEXO's simulation framework. And the procedure here It's pretty simple. We start with our Monte Carlo truth light map. We then sample that to get a bunch of calibration events, which have some position that we've measured and some associated light collection efficiency that we've measured. From there, we take this set of calibration data and we try and reconstruct the true light map. And then we can compare the reconstructed light map to the Monte Carlo truth light map and see how well the calibration works. So there are many different ways to do this step of reconstructing the light map from our calibration data, and I'm going to talk about some potential ways that you might do this. One is to use a histogram. So you just histogram. You just basically take the light collection efficiency that you measured in each voxel and create a histogram. The problem with this is that you get really poor resolution if you don't have enough events to fill up all bins, or else you get really large bins. Another way to do this would be to use kernel smoothing instead. The problem with this is that the kernel smoothing algorithm requires you to calculate a bunch of pairwise distances between all these calibration events. So for large data sets, this just becomes really computationally inexpensive, really fast. So the alternative that we settled on is to use a neural net, and that avoids both these problems. It's really fast, it scales really efficiently, and even works for small data sets. So this is kind of an overview of my design of a neural net for this process. The neural net takes in the XYZ position of an event within the TPC and is trained to output the collection efficiency. It's just a multi-layer perceptron with 5 hidden layers. And part of this process, the process of designing this involved doing an optimization over a bunch of different hyperparameters to make sure that the architecture was optimized for our ultimate goal. And then the actual, the final light map that we produce from this is the average of 5 light maps trained on our calibration data. So here now I'm showing the light map calibration for performance. So the color scale is showing the relative light map error. So we want to avoid these regions of red and blue, which indicate large errors. And so you can see that when you start with 1,000 events, 1,000 calibration events, you have pretty significant errors, especially at the top and bottom and around the edge of the TPC. And as you increase the calibration data set sizes, those errors recede to the point where with 1 million events, especially in the inner 2 tons, which is our most sensitive region, that's denoted by this, this red dashed line here, we get quite low reconstruction errors. If you actually want to quantify this, you can do that on plots like these, where I'm showing the light map error as a function of the number of events, both in the active region, so the full xenon volume, and the inner 2 tons, which drives our sensitivity. You find that we get less than 1% error in the full active region after around 2 weeks of calibration data. If you then translate this into energy resolution, into the contribution of this light map error to our overall energy resolution, you find that after a few days of calibration, the light map error term has a negligible contribution to the energy resolution in the inner 2 tons without any requirement for detector downtimes. The nice thing about this is that we can just do this while we're taking data and get in our most sensitive region no worsening of our energy resolution. And that was published in 2022 in GINST. Okay, so that's the charge and light calibration piece. Now I'm going to move on to identifying and mitigating background sources near the Q value. And so my work on that involved designing a xenon purifier for nEXO. So xenon purification is done in the gas phase. The basic process is that we boil off xenon from the TPC, force it through a getter purifier with a pump, and then recondense it back into the TPC. And the purification occurs when impurities in the xenon are captured on the surface of the getter material in our purifier. And this works based on the fact that certain group 4 elements like titanium, zirconium, and hafnium are really good at absorbing impurities onto their surface and actually dissolving them into the volume of the metal. These purifiers are typically operated at high temperature, which allows us to break up heavier compounds in addition to things that are dissolved more easily, like oxygen and carbon dioxide and methane. The problem with this is that these purifiers are known to be a source of radon emanation. So the reason that matters is that radon is a background which, if it shows up too much, could be a problem for nEXO. So just to give some background, radon is produced by the decay of radium-226, which is the daughter of the uranium-238 decay chain. Radium tends to bind to solids, so it's not going to go anywhere once it's produced in the getter material. Problem is that the daughter, radon-222, is not strongly bound to the solid matrix, and so it can escape into the gas and it can flow into the TPC. So we can get this transport of our radioactive material from the getter into the TPC. And the specific reason we're concerned about this is that further down the decay chain, there's this gamma background at 2.448 MeV, which happens to be very close to the Q value, which means that it's very difficult to separate from the neutrino beta decays that we're interested in seeing. So purification is typically done with some standard materials, and the one that's been used in the past for a lot of these types of experiments is ST707, which is an alloy that is used in the commercial purifiers made by SEIS that are often used for this purpose. It's an alloy that has about 70% zirconium, but it also has other metals in the alloy as well to increase the interstitial spacing in the matrix and enhance diffusion of these impurities that are captured on the surface into the bulk volume of the matrix. It's also sintered, so it has a really large surface area, as you can see on this SEM image with 50 micron scale bar there. And in addition to that, it's operated hot. So the whole purpose of, or the reason for all of these things is to increase the capacity as much as possible to ensure that these impurities can be dissolved into the bulk volume of the metal. The problem is that we suspect that the more efficiently things are dissolved into the metal, the more efficiently radon is released from the metal. This could be a problem for nEXO. So my work was on using pure zirconium, high purity zirconium as an alternative to this. We hope that it would have fewer radioactive contaminants in addition to some of the other aspects that I'll talk about, including a much lower surface area, as you can see from this image here. This, in principle, should result in less efficient transport of radon that's produced in the solid into the flowing gas, and therefore result in less background sources in the TPC. We also think we can operate this at room temperature, which means that we don't get this dissolution of impurities into the bulk volume very efficiently. But once the surface has been saturated with impurities, we can do these regular bakeouts to regenerate the surface. And so my work was on building a custom purifier to demonstrate some of these things. So there are a few different things that you'd want to consider when designing such a purifier for nEXO, including fluid flow, surface regeneration, and how efficiently it actually purifies, and its concentration of impurities or radioactive impurities. I'm not going to talk about the first two, so I'm just going to focus on the last 2 points here. This is just an overview of what the design of this purifier looks like. So we have this column of zirconium pellets packed in between these two sintered stainless steel filters and held in the middle of this long conflat tube. On the outside is this aluminum clamshell surrounded by a band heater, and the purpose of this is to allow for an in situ bakeout of the getter surface to do that regeneration. These are just some photos of the assembly process. So these are the pellets, the zirconium pellets being loaded into the purifier body. And then on the right is the purifier itself plumbed into our system in the Stanford lab. So the purification efficiency measurements that we did were all done up at SLAC with our collaborator there, Peter Brosen. And there they have a dedicated facility, the xenon purity monitor, or XPM, where we get real-time measurements of the xenon purity, which is really useful for what we're trying to do. So the procedure that I followed is to start out by injecting air into the flowing xenon. The purpose of this is to destroy the purity, essentially. We can then repurify the xenon at first with the SEIS commercial purifier. We then repeat the process, inject more air, and then purify with the Stanford custom purifier, or SCP. And then using the data we get from both of these, we can fit the purification efficiency from a model, which allows us to extract the efficiency of the custom purifier. So this is an overview of what the data looked like. The purity I'm showing in electron lifetime, so higher electron lifetime, it's better purity. We start out initially at around 3 milliseconds, which is quite good. We then dose with air, and the purity immediately drops off quite significantly. We then recirculate the xenon through the SEIS commercial purifier, and the purity climbs. We inject air again, and the purity drops, and we recirculate through the custom purifier, and again, the purity climbs. And so we can then fit both of these phases that are shaded in green and purple here to extract the purification efficiency. So the actual model that we're fitting is showing the evolution of oxygen-like species or impurities in the xenon as a function of time. And we consider addition of oxygen and other stuff like that via outgassing, and then removal via purification. And so this depends on the recirculation timescale. It depends on the efficiency, which is the thing that we're trying to measure for the purifier. And it also depends on this equilibration factor F, which is just a geometric factor that describes how quickly changes in purity will propagate through the full liquid xenon volume. And so that's a detector specific thing that we didn't know in advance, we had to measure. So this is the reason for doing this with the SEIS commercial purifier first, because we know the SEIS commercial purifier has an efficiency that's roughly 100%. I mean, for all intents and purposes, it's 100%. And so that allows us, by setting this to 1, to extract the equilibration factor F. So then when we repeat this with the custom purifier, now knowing F, we're able to fit the efficiency. And we find that the efficiency is about 84%. So it's not at the level of the commercial purifiers, but it's still quite good. And just based on this, we can kind of make up the difference by tweaking the recirculation timescale if necessary. So now I'm going to talk about the radioassay measurements, which are really addressing our main motivation for doing this, for developing this purifier in the first place. So we did a number of different types of radioassay measurements of this high purity zirconium material, and I'm not going to go through all the results, but the one takeaway that I'll share is that we found that the radon emanation is higher than NEXO's target, and it's actually similar to the commercial purifiers. So our main motivation for doing this actually turns out not to be true. This is not lower in radon emanation than commercial materials. But there is one upside to what we found, and that's that the ratio of the solid radium-226, or the activity of the radium-226 and the radon-222 appears to be roughly 1. What that means is that all of the radium decays in the solid are resulting in radon escaping into the flowing gas, which sounds like a bad thing, but given the fact that this is a solid metal, what it tells us is that most of the radium is probably concentrated on the surface of the metal, just as a result of the production process. And so our hope is that we can bake it off. Radium has a higher vapor pressure than zirconium, so you can actually heat this up to about 1700 degrees Celsius and evaporate off the radium from the surface. So we're hoping that this will allow us to produce radio pure material for our getters. We're currently doing work in collaboration with the nEXO group at PNNL to try and do this, and they're currently doing some small scale tests with these individual pellets of zirconium in an electrothermal vaporizer, and then analyzing the removal of barium, which is a surrogate for radium that's a little bit easier to measure. And we hope that eventually we'll be able to do a full-scale test and then redo the radioassay measurements and determine whether this actually worked to reduce the concentration of radium that's going to be potentially problematic, or we'd use this in nEXO. Okay, so that's the end of part 1. So I'm going to completely change topic now and talk about micron-scale interactions. And I'm going to start with something that's I think very familiar to all of us, and that's Newtonian gravity. And so what I'm showing here is the potential energy of a configuration of 2 point masses that are separated by distance r. And the plot here is just showing the field strength as a function of the radial distance from one of those masses. And this straight line on the log-log plot here is just showing us the really familiar inverse square law. What we're interested in is a modification of gravity, or an effective modification of gravity that we get from some new type of interaction that we're parameterizing with this Yukawa term. So that has 2 parameters, alpha, which is the strength relative to Newtonian gravity, and lambda, which is the length scale of the modification. And the interesting thing about this, as you can see here, is that at length scales above this length scale lambda, this is really invisible. You just see something that looks like gravity until you get to short enough length scales that it turns on. And then it becomes really obvious. It can be, many orders of magnitude stronger than gravity. The fact that we're using a Yukawa potential may seem somewhat arbitrary, but from the perspective of particle physics, it's a pretty natural choice because it describes an interaction mediated by a boson with a mass that's related to this length scale. So it's actually a fairly general class of new interactions. And there have been many different experimental tests of modifications of this type. So here I'm showing the full landscape of these measurements with the strength parameter alpha spanning some 40 orders of magnitude here. And then on the x-axis, lambda showing about 25 orders of magnitude. So clearly, this has been done with a variety of different sensitivities at different length scales. I'll point out a few of interest. So the first is the place where we're best at doing these types of measurements. And that's at the scale of roughly the Earth-Moon distance. The reason for this is that the retroreflectors left on the moon by the Apollo and Luna missions can be used to do laser lunar ranging, or in other words, to precisely map out the distance between the Earth and the moon throughout a full orbit. You can then set limits on the anomalous precession and translate those into limits on this Yukawa-like modification to gravity. So that's where we have something like better than a part in 10 to the 10 sensitivity to these potential modifications. So as you go to shorter distances, the sensitivity gets much worse. It's just in general hard to measure gravity at short length scales because it involves putting massive objects very close together. There have been experiments that have done this on the scale of tens to hundreds of microns, and I'm showing the Edwash torsion pendulum here as an example. So they do this by taking this rotating attractor, which, as you can see, has these holes to create this density pattern, which they can then rotate with a very short face-to-face separation between that and their torsion pendulum, and they can directly measure the torques from the gravitational force. And they do this at a face-to-face separation of about 52 microns. So this allows them to search for new interactions at 52 microns and below that by kind of extrapolating based on choosing different values of lambda and computing the resulting force at that separation. But given that their separation is limited to 52 microns, their sensitivity falls off very quickly. So that's the best measurement of gravity to date in the lab at these length scales. It's a 52 micron face-to-face separation. If you go to even shorter distances, you get another type of experiment that's using a somewhat similar technique. So again, they have a density pattern attractor that's rotating in proximity to a test mass. And their face-to-face separation is 200 nanometers, but there are many orders of magnitude for measuring gravity at some point. So just in general, I'll point out that the techniques that are doing this type of measurement on the length scale of a few microns or tens of microns are all using mechanical springs. And they're all systematics limited at this point because no one's been able to measure gravity at shorter than 52 microns. So given this, our group has been interested in developing alternative techniques that we hope can complement these existing techniques. And in addition, our techniques are subject to a completely different set of systematics we think adds value to this program in general. And so that's what I'm going to talk about next, is our search for new interactions using optically levitated microspheres. So the way that we do this is we create an optical trap using a vertically oriented 1064 nanometer focused laser. We can then trap a microsphere at the focus of this laser. It's essentially sitting in a harmonic potential with a spring constant of around 10 to minus 6 newtons per meter and resonant frequency of about 400 hertz. We then need an attractor to source potential interactions. And so like the experiments that I just discussed, we need something that has this density pattern. And for us, we use these alternating fingers of silicon and gold to create a strong density contrast. Because we're interested in in gravity and not electromagnetic interactions, we place this gold-coated shield in between the two to mitigate any electromagnetic interactions between the microsphere and the attractor. And if you look from the side, this is what it looks like. So we have about a 6 micron separation between the edge of the attractor and the face of the microsphere with the shield in between. We can then oscillate the attractor at 3 Hertz to source a time varying force on the sphere. So just for context, because I'll come back to this in the future, the Y direction, when I say Y, I'm talking about the direction in which the attractor is oscillating. Z is the direction of the beam, and X is perpendicular to both those. And so this is what it looks like in kind of a cartoon version. When we apply this time varying force to the microsphere moves in this trap in response. That deflects the trapping laser beam, which we can then read out on a quadrant photodiode. So essentially we got 4 different photodiodes that can tell us about the deflections of the trapping beam. This allows us to reconstruct the force on the microsphere. And so we get a time series that looks like this. And as you can see, this is kind of a complicated time series that's just a result of the geometry of our attractor system. So just for some context, I did analysis for this project. I kind of joined this project, I think probably close to 2 years ago. And so as my role is mainly in analysis, my overview of our search is going to be very biased in favor of the analysis perspective. So from my perspective, we have signal templates that we can compute for a Yukawa interaction with the attractor. We can take force measurements in both the X and Y components of the force and at multiple different harmonics of the attractor drive. And then given these signal templates and the force measurements, we fit a scaling parameter that best matches the templates to the measurements. And that allows us to report either discovery or set a limit on the scaling parameter. So the advantage of the type of experiment that we're doing is that we have this really complicated signal template in which we can try and search for both for signals at both the correct magnitude and phase in order to make a discovery. So we compute these templates by doing a finite element analysis over the geometry of the sphere and the attractor for a bunch of different relative positions. And then we can compute based on the stroke of the attractor in proximity to the microsphere, what the response should look like at multiple different harmonics. So here I'm showing a few different frequencies, both the X and the Y components of the force. The signal power based on the geometry of the attractor is distributed into many of these harmonics. So we're looking for something that shows up at multiple different frequencies, more than just the 4 that I've shown here. And this gives us a really distinct spectral fingerprint to match our measurements to in order to clearly identify a signal or reject something that's not a signal. Just to give a quick overview of what our actual data collection process looks like. Of course, before we collect data, we have to calibrate the microsphere force response by applying a known force electrostatically. We weigh the microsphere, we discharge it to neutral, and then we take data in repeated 10-second iterations for about a total of 14 hours. And our force sensitivity is around 10 to the minus 17 newtons per root hertz. So now I'm going to show what our data look like. So the data are shown as a histogram in blue here. And so if you just looked, for instance, at this one plot here, you'd say that your data is actually really matching well with your signal template. It's consistent with alpha of positive 10 to the 9, so that's an attractive interaction. But of course, this is the reason why we have multiple different harmonics and components of the force to look at. Because if you look across multiple different harmonics and both the X and Y components of the force, you see that it's not consistent across all these harmonics and components. And so what we're seeing is actually not a signal. And so rather than claim a discovery, we can use this to set a limit on Yukawa interactions. So I'm going to talk quickly about how we can do that. So as I mentioned, we're measuring the force in each component, which I've indexed by K, for each harmonic J, and for each of these many different 10-second data sets I. This is a complex amplitude, so it includes both magnitude and phase information. We have a template for each of those as well. And we want to find the alpha that best matches the template to the measurement. And so we can put this in a Gaussian with our uncertainty given by our noise, which we measure with the attractor stationary. And then because we have both amplitude and phase information we want to use, we do this once for the real part, once for the imaginary part. And this constitutes a likelihood function for a single one of these integrations at a particular harmonic for a particular force component. It's often easier to work with log likelihoods than likelihoods. So here what I'm showing now is a type of log likelihood, or the profile likelihood ratio, for a number of these different harmonic and component combinations. And on this plot, you can just read off the minimum of the negative log likelihood, what the best fit value of the scaling parameter alpha is. And again, you can see that because we have some best fits at negative alpha and some at positive alpha, what we're seeing across different harmonics and components is not consistent with a single new interaction. We can combine these to give a global fit, but again, this is not consistent with zero. So we're measuring backgrounds that look like something non-zero even after we kind of average over all these different harmonics. And so we want to set a limit, and we use a test statistic that allows us to do that without claiming a discovery. And that sets an upper limit on this strength parameter alpha for each value of lambda that we test. Yeah, so here I'm showing our results from 2021. So just for context, the first data with this setup was taken in 2020. The results were published in 2021. And these are the limits that I'm showing in this plot here. So that was the first ever measurement of, or the first ever test of Newtonian gravity at these length scales using optically levitated microspheres. We learned a lot from that process and then made some upgrades to the system, which are going to be reflected in the improved limits that I'm going to show. So the statistical procedure that I just showed, we applied to 10 data sets from last fall from 3 different microspheres. We did this fitting process on 6 harmonics for both attractive and repulsive interactions in both the X and Y components of the force. And that gives us improved limits, which I'm showing now. So we improved by about a factor of 50 at 10 microns, which we've written up in a paper that's now in the archive and under review with PRL. And so, yeah, as you can see, we're kind of closing the gap between our previous results and the state of the art that's done by these mechanical spring-based experiments, but we still have a ways to go in order to break into that new parameter space. So as I mentioned, we're limited by backgrounds, and I'm going to spend the last little bit of my talk discussing some strategies for reducing these backgrounds. So to start, I'll address electromagnetic backgrounds. We know that our attractor and our shield, or in fact, we set our attractor and our shield to be grounded to the same point, so they're in electrical contact. What that means is that the Fermi level is the same throughout both materials, but if the surface properties are different, in particular, if the work function is different between these two materials, we can get a contact potential difference between the attractor and shield, which results in an electric field that can be measured at the trap focus. And so this can cause a background because our sphere has no monopole charges, but it can have electric dipole moment. And the result of this interaction between the dipole moment and the electric field is a force on the microsphere. So we have a technique that we can hopefully use to subtract out these backgrounds. I'm showing here a sample spectrum of what these backgrounds might look like from an interaction between the dipole and the electric field. And because the electric field is being modulated at the frequency of the attractor drive, we get harmonics, we get the background showing up at harmonics of the attractor drive here. But one thing we can do is we can modulate the bias between the attractor and the shield. So we no longer ground them together. We apply some time varying bias between them. And the result of that is that in addition to getting the usual background spectrum, we also can produce 2 copies of this background spectrum at the sidebands of our modulation frequency. And the advantage to this is that this gives us background witness channels in which we can measure this background spectrum and then subtract it out at the frequencies in which we're actually doing our physics search. The reason that this can work for us is that the Yukawa interactions will not couple to the bias in the attractor And so they will not appear at the sideband. So none of the physics, the interactions that we're interested in are going to show up at these sidebands, which means they really are clean background witness channels. And the advantage to this is that we get the full spectral fingerprint of the backgrounds that we can then match to the spectral fingerprint that we measure in our harmonics of interest. So we hope that this can be used for in situ background subtraction. We've done a first test of this with a 200 millivolt peak-to-peak bias modulation applied between the attractor and shield. And so that bias frequency is shown in red there, and the sidebands are shown in orange. And you can see that we actually do see these at these first two harmonics, the response of the dipole interacting with this field. But you can also see from this plot that these are much lower amplitude than these other spikes that are not at the sidebands. And in fact, those are our other backgrounds that are really limiting our search right now. So we think at some point this will be useful, but for now, the other backgrounds are so much higher that this is just not going to be of much use to us until we can remove that other source of backgrounds. And so that's what we're going to talk about now. We know these backgrounds come from scattered light, so stray light that's scattering off of the moving attractor and then is being detected by our quadrant photodiode. We know this for a few reasons. It's there when the attractor is oscillated even without a sphere trapped, so it's not sphere motion we're seeing. It decreases as the attractor is retracted away from the trap focus. So I'm showing that in this plot here. As we increase the separation, the background falls off. We can block it by an aperture. So the other thing that this plot is showing is that when you put an aperture at the focus of a telescope in our output optics and essentially block out the outer part of the beam, these backgrounds go away to some extent, at least. And so we know that this is not real sphere motion. And then another really convincing piece of evidence is that when we blacken the attractor by coating it with platinum black, these backgrounds decrease significantly, but they weren't completely eliminated. So to address this, I'm going to discuss how we can do our microsphere position measurement and how we can use this to construct a data stream in which we can monitor these backgrounds in situ. So if you have a quadrant photodiode, so four sensors arranged in this configuration, and you want to measure deflections of a Gaussian beam, the naive way to do this is just to take the top amplitudes minus the bottom amplitudes to get the Y position, and the right minus the left to get the X position. There's actually two additional linear combinations of these sensors that you can use, or that you can come up with, which in principle should not show any motion of a Gaussian beam. In reality, of course, we're not using a perfectly Gaussian beam. We're using a beam that has interacted with the microsphere and has this complicated scattering pattern from this interaction with the sphere. And so really what happens is we get this coupling of the microsphere motion into these non-physical channels. And so what this tells us is that we can do some calibration to optimize the way that we're measuring our position. And so we can calibrate to known motion in the microsphere. So the way that we do this is by using the X and Y resonances of the microsphere. So we know that the microsphere is in a harmonic trap in both X and Y. These have slightly different resonant frequencies. So these two physical modes in which the microsphere can move is then measured on 4 sensors. So if you want to do this calibration, you're taking your 4 sensor amplitudes, you're applying some calibration matrix, and you're getting out the X and Y motion. But you'll notice, this is a non-square matrix, and the reason for this is that when you're going from 4, when you have 4 sensor amplitudes to measure, you can actually construct more than just X and Y. You get all 4 of these data streams, including both the position and the non-physical modes as well. And so the nice thing about this process is that in doing this calibration, in addition to producing clean X and Y data streams that show the motion of the microsphere, we get these 2 additional channels that have been calibrated to not see microsphere motion, so we can use them to witness the backgrounds. So here I'm showing our 2 resonances in X and Y before the calibration, and the brown is showing the null stream, so that's one of these 2 data streams that in principle should not see microsphere motion. As you can see, before the calibration, it is seeing cross-coupling from both X and Y. After we do this calibration, the motion disappears from the null stream. And so this tells us that our null stream is free of microsphere motion, and it can be used to witness our scattered light backgrounds. So the way that we would use this is, let's say we take data that looks like this. Okay. So we have a number of different measured forces or apparent forces above the noise after 12 hours of integration time, and we want to know if this is real force. So we can check the null stream and find that in fact what we're seeing is not a real force, because our null stream, which doesn't show any microsphere motion, is showing something above the noise at every single one of these harmonics. It'd be really nice if these spectra matched precisely, so we could just do background subtraction. It doesn't work quite that well. So for the moment, this is kind of used as a diagnostic tool for us to monitor these and understand how much they're showing up in different configurations. Yeah, I'll just summarize what our progress on this search has been. So we're currently limited by the scattered light background, but we have this calibration technique, which in principle we can generalize to a larger sensor and hopefully get better discrimination of the true microsphere motion and scattered light. And in parallel, we're also working on developing an enclosed attractor system that doesn't interact with the light field. And provided we can improve the scattered light backgrounds, we hope to be able to use this technique for electromagnetic background subtraction to do in situ subtraction. And we hope that that'll be possible once we're not dominated by the scattered light backgrounds. Yeah, so maybe I'll just skip past this and acknowledge all the work that our many collaborators, both with nEXO and in the microspheres group, have put into this project. So I want to thank all of them for their hard work on this over the last few years, and thank you for your attention as well.
Nice talk. For a few questions.
Yeah, so I think you did explain it, but I didn't quite catch it. On slide 119, you explained how you made the Yukawa templates, but I didn't quite follow.
Yeah, so basically what we're doing, so we just have a finite element, like we have essentially a model of our attractor and our sphere just done using a finite element analysis. And then just point by point on each, we can compute the potential between the two and integrate over both bodies, and that gives us the potential of configuration. And so we need to do that for both, for essentially every possible relative position of the attractor and microsphere. And so when we do this calculation, we get the potential at every possible configuration. Then what we can do is we can take the real digitized drive of the attractor and sample our grid of potentials, and then just grading the potential gives you the force. So we just use the real attractor motion to sample this grid of our pre-computed potentials between these two objects. And that gives us the force.
Thank you.
So back to the like light calibration on nEXO.
Yeah.
Do you know why in like I think going further down?
Back here.
No,
Or
like
this way?
yeah. There was the plot with like the reconstruction differences. Yeah,
Yeah.
that one. Why, you know why like the sort of events in large R are doing so bad in like the 10⁻³ event region, like why those aren't getting reconstructed well? Because those are where the light collection efficiency is the highest. So I would think those would do the best.
Yeah, the large R, I'm not so sure, but I know, so it tends to be bad where there are steep gradients in the collection efficiency.
Okay.
That may have something to do with it.
Mhm.
Just if you're not sampling across the gradient well enough, which you're not, if you have too few events, you don't
Okay.
really
Yeah.
reconstruct it that well, because the neural net tends to want to make things smooth and non-changing. Unless you have a lot of events telling it you actually really need a steep gradient here.
Okay, yeah.
So that's my guess.
Great talk. So maybe a follow-up on Jackie's question. I'm wondering, do you have a good model for your background? Or if not, how do you trust your likelihood fit?
Yeah, so we don't have a model for our background. We've been trying to think of ways to do this. It's really kind of not a trivial challenge. It seems to depend less on kind of the macroscopic geometry of the system and more on just microscopic features of the attractor surface itself, because it's scattering light. The backgrounds tend to change over time. They change from data set to data set. They depend really finely on the relative position of everything. So overall, our picture of the background is that they're just not amenable to modeling, unfortunately. So this is why we're trying to do this type of in situ measurement. So in terms of how that affects our likelihood fit, I mean, we're doing our analysis. We're essentially doing a signal only fit to data that includes backgrounds. And so there's really no well-defined statistical procedure that I know of that can make this really robust. So we kind of settle for doing things like Monte Carlo tests of signals with injected backgrounds to make sure that our coverage is approximately correct. Because there are ways to do the likelihood analysis that will subject you to significant undercoverage. And so we just say, okay, like we're never going to be able to do this perfectly because there's not really a way that exists to do this in the presence of unknown backgrounds. So we're just going to try and get our coverage as close as possible to what we report.
Yeah, I think Andy has his hand up. Andy, do you have a question online?
I do. Does the Casimir effect make a nonlinear spring in the X direction? And probably that's too small compared to your light spring, but why are the resonant frequencies different in X and Y?
Yeah, so there's a small amount of astigmatism in our trapping beam, which we think causes the different resonant frequencies in X and Y. Casimir is, as far as I know, is much smaller than something we can measure, so this isn't affecting us at the moment.
Okay,
We also have the shield there as well, which mitigates some of that.
Okay, maybe one last question from Tom.
So this null channel that you like calibrated away, I didn't fully understand that. So you just take a measurement with the particle in the trap and you see this motion.
Yeah.
And then you take a measurement without the particle in and you say this is what it should look like, and you calibrate it that way, or how do you know what it should look like, I guess is what I'm asking.
So what we do is we use the fact that our resonances are separated in frequency. And so the true motion, or the thing that we say is true X motion, is just the amplitudes that we get at the X resonant frequency, and Y likewise at the Y resonant frequency. We call those four amplitudes true Y motion. In reality, I mean, depending on the pressure in the system, you can see that these Lorentzians are going to be kind of interfering with one another to some extent. So we do get some XY cross coupling, which we can quantify in our calibrations later on. So that gives us X and Y. We essentially get a set of four amplitudes that correspond to X and four amplitudes that correspond to Y. And we're just calibrating those to the identity matrix, which tells us that we have all X in one channel and all Y in the other channel. But because we're doing this calibration of our four sensors down to the two physical modes, it's just a linear algebra problem at that point to find the two remaining orthogonal linear combinations. So once we have X and Y, we just take the two vectors that are orthogonal to those combinations of the quadrants, and that gives us these channels that in principle shouldn't see microsphere motion. And then we check that by looking at the transfer function calibration data to make sure we're actually not seeing motion in those channels.
Right, and that so then this graph here, that is that, but after that procedure, you get the brown line for the.
Yeah, we just get like a noise. Yeah.
Okay, so let's thank Clarke again.
Related to that, on the rectify, one more actually. Yeah, so is this FX already after applying that calibration? So the like null data should already be subtracted out of FX if the calibration were ideal. Or
No, so the reason is that the motion doesn't couple into the null channel over the scattered light channel, but scattered light couples kind of evenly into all four. So scattered light will always show up in all the channels, whereas motion will be confined to only the two-dimensional XY plane. So
I guess so. Yeah, okay, so the calibration puts all motion into X and Y, but I see, but not all non-motion into non-X and Y.
The way that I think about it is the scattered light, who knows what the scattered light's doing? It's just so complicated. So I think about it like it's a four-dimensional vector that's just kind of doing something over time.
Yeah,
And you're just looking at the projection into X and the XY plane. That's our X and Y measurements, and then you're looking at the projection into an orthogonal axis, and that's this one. And in theory, if without some physical understanding of what's going on, there's no way to infer what's going on in X from what's going on in an orthogonal projection.
So you can't really do a coherent subtraction. You would just be able to attribute some of the power that you see
Yeah,
in X and Y, assuming like this orthogonal basis is like getting an even distribution of noise power across the whole basis.
yeah, that's basically it. I mean, one thing we know is that these are always in phase, like the phase relationship is fixed, so that
Oh.
takes away 1 degree of freedom between the null channels and the XY channels, but yeah, we don't like, we did a lot of work to try and understand this coupling between these different channels, because once we kind of understand that once, we hope we could then apply it and do background subtraction at some level, but for the moment, it's just like a proxy for how much power we're seeing.
I'm a little surprised that the noise, that the phase is the same between all of between the channels. Should I be? Is that?
More than it's just, so it's not, it's, let's see, so if you
Or
look
it's
at.
fixed.
It's, yeah, so let me just go to the templates. Which I have somewhere here. Okay, so these are the templates. So at each harmonic, we know what phase the attractive Yukawa should show up in, and we know what phase the repulsive Yukawa should show up in. The null channel shows measurements in phase either with this or with this, so it's either in phase or 180 degrees out of phase, but there's no kind of, there's no sort of in between here. Yeah, physically, I don't know, I've thought about this before. I can't remember at the moment what my conclusion was, but I don't think I was ultimately too surprised by this.
This is just from the scattered light, not from the sphere, right? Still,
Yeah, this is scattered light, yeah.
so you wouldn't have to take into account the phase shifts from measuring a frequency off of the resonant frequency of a harmonic oscillator.
No, I mean, we're just measuring everything relative to the phase of the attractor drive, and everything's in phase. Yeah.
I guess maybe I would say Ben's question in that, like, as the if there's one of these like background drives, like as it sweeps through the, like as a real force on the sphere sweeps, as that sweeps through the resonance, its phase should flip. But as an apparent motion sweeps, its frequency sweeps through the resonance, it's not actually filtered through the mechanical response, and so its phase is the same
Right,
the whole
right.
time. So is that is that the behavior of this, like these scattered peaks that, or like, do you get
So
some
yeah,
information from that?
the problem is,
way some resonance.
yeah, so we're working at like
Right.
up to about 40 hertz, and our
Right.
resonant frequency is 400.
But why not go all the way up to resonance? I guess you just can't move the tractor that
We
fast.
can move the attractor much faster than
Yeah.
we're doing right now.
Small, but it's the point. But the fingers have to be big compared to separation distance or something like that. So,
So I mean, I kind of think it's a good idea at some point to do the search at the resonance. Because scattered light shouldn't be amplified at the resonance.
and it gives you this very characteristic mechanical response.
Exactly,
Which maybe
exactly,
doesn't help you orders of magnitude, but gives you another factor of a few on top of everything else, right?
Yeah.
Is there any leakage of the Z signal through the calibration since, I mean, or is the Z cold enough and the attractor flat enough that it shouldn't be coupling?
So there is some cross coupling with Z in terms of how we do this. This construction of the of our signal streams and our null stream, or XY streams and our null stream. We construct this matrix that describes this coupling, or this how you get from the 4 quadrant amplitudes to the XY and then the 2 null channels. And if you look at the singular values of that matrix, that tells you kind of the number of effective degrees of freedom in your system. And it appears that it's very close to 2. Like we have 2 singular values that are roughly the same size, and everything else is like 3 orders of magnitude smaller. So that's kind of telling us that we're like, by doing this calibration, we're effectively seeing just X and Y motion and maybe some cross coupling that's really, really subdominant. I mean, it's always there at some level, but in terms of how we're using it at the moment, it doesn't seem to impact us. In principle, we could do the force search in Z as well. by just introducing an offset between the attractor and the microsphere, but for now, we're just doing it in X and Y.
I'm curious if you like insert a piece of Clarke Hardy reflective surface between the attractor and the sphere, would that be easier to model for the scattered light?
What do you mean if like the,
If there's any stray reflection, it would be reflected off the mirror rather than the attractor, and that doesn't affect the gravity signal.
yeah, I mean, we have this shield, which is pretty reflective in between right now. The problem is like, so ideally we'd have something that's completely shielding the attractor from any interaction with the light field.
Yeah, but what
And then-
can you imagine, laser hitting the sphere and the photon bounce back and forth between whatever is around the sphere
Mhm.
and eventually make their way into the photodiode. Those kind of things could be very difficult.
Yeah, I mean, it's difficult to model for sure. I mean, the only, like, the backgrounds are only showing up in phase with the attractor drive
Right.
3 Hz. So any kind of weird interactions between the sphere and the shield or other parts of the system, in principle, shouldn't show these backgrounds. It really has to be some interaction with the attractor. It's just difficult to shield the attractor completely. It's hard to build like something to enclose the attractor without cutting too much into the trapping beam, while keeping the attractor close.
So do you mean, so yeah, the question, like, if you just put another piece of metal, like, it looks like it was like blocked off from below, if you just put another piece of metal on the top there, like, I just don't know what's
Yeah,
physically going on around this.
I mean, that would be like, it's a very sensible thing to try and do. And one of our postdocs at one point kind of sat down and tried to see if he could glue two of these shields together to enclose it completely. It's just a really large aspect ratio device and it's really thin. It's like 3 microns thick or something, and hundreds of microns wide. So it's just a structural problem that you want to keep it, like you just kind of want to glue it there. You want everything to be parallel to within like a micron over hundreds of microns distance. I mean, maybe there's a way to do it, but we just haven't managed to figure it out yet.
Yeah, sadly, we were also going down this road of shields for our shields.
Yeah.
At the point, like, we decided it was getting too hard for us.
Yeah.
Shield to shield. But yeah, I mean, this is really beautiful stuff. To see, after knowing how hard this is, to see continued improvement here. So,
Yeah.
and like, it's really actually great to see the background understanding.
Yeah.
Like, it's not the dipole, it's the scattering line.
Yeah.
I have a feeling the camera, like, imagers are gonna really beat that.
Yeah, I mean, our running joke is that every time we tell a particle physicist about our problems, they say, "Oh, just get like a high pixel density and
More
like, do
channels.
some machine learning
I mean,
and you'll have it
with
in no
your 4
time."
channels and like it gotta, like,
Yeah,
you're
yeah.
already getting something with,
And
I
just,
don't know how it scales the number of channels.
well, just based on this picture that I brought up about, you have some random vector that's doing some crazy stuff you don't understand in 4 dimensions, and
Yeah.
you're measuring a projection into 2 dimensions.
Yeah.
Now make that 100 dimensions,
Yeah,
and
exactly.
the projection into 2 is just gonna be much smaller.
Yeah.
So you don't even maybe need to subtract the backgrounds at that point. You just construct a sensible linear combination of your pixels that gives you X and Y with very little.
Exactly, which our eye, I guess, is doing as we watch that thing move, like,
Yeah.
you're not gonna get confused by the scattered light.
Yeah,
The
exactly.
photodiode does.
Yeah.
So yeah, I mean, that'll be very impressive if you get that photodiode array going.
Yeah, it's a work in progress, so.
Whatever happened to this little spinning wheel too?
Oh, there's that, yeah, we
Because
have,
that's another way to get it up to frequency, I think.
yeah, so we have the rotary attractor. I think we have a bunch of these that were fabricated. There was an undergrad working for us on this, and he has since moved on to grad school and no one's really picked it up. And we're not really sure if it's kind of if it merits enough attention, given that we have so many other challenges at the moment, so.
Yeah.
Is 6 micron absolutely necessary here for this measurement? Make the attractor a lot heavier, so you can move it away from the sphere a little bit.
We can move it away a little bit, yeah. Unfortunately, the scattered light backgrounds and the signal strength fall off at roughly the same rate. So we actually don't get much advantage from moving back. In principle, it's always better to be closer. If you're background limited, just get close enough and then kind of do the same no matter what you do. So yeah, I mean, if we have kind of tried that to see if, we've also like, depending on who you ask in our group, some people will tell you that if you look at the backgrounds as a function of separation, you can see fringing at maybe like some multiple of, or yeah, some, I don't know, fraction of the wavelength. Indicating there's some diffraction happening around shield. I don't really buy it. I think you're just like fitting by eye and being deceived by it. So in principle, maybe there's a nice way to model this and understand it better, but we're just not at that point yet.
Yeah, there was some funny like oscillation in the chameleon paper, and some theorists took that to like some oscillatory.
Oh, yeah.
Force.
Yeah.
On the, you had a plot of like what the Yukawa potential does close to the beginning. And it was like this log plot of the 1 over R law, and then with the, yeah, so I just did the math, like the log wrong, but like, why does it go back to 1 over R below this dotted red line? So like, why don't these searches just like, yeah.
You're effectively, if you're probing in length scales much smaller than lambda, you don't see a change in the force. Like, so when you go from, so if lambda's here is 10 microns. When you move by a micron, in the field of something that falls off with a lambda of 10 microns, you're just not changing the force that much. So effectively, when you get to really short length scales, the force is just constant, so it's effectively just modifying G. So G is now larger by a factor of 10 to the 6.
Oh.
And as you change the distance on sub lambda scales, you see no change.
I see, yeah, because the R and the R cancel. Yeah,
Yeah.
okay, gotcha.
Yeah, I think, 10 microns is also like that 6 micron separation. In principle, given the existing limits, 10 microns was the lowest hanging fruit.
Yeah.
Because it's like below at wash, but not impossibly hard to measure gravity below.
Yeah, like if you look at the existing contours, there's like a little sort of corner at about 8 microns.
That
where-
notch used to be a lot better before that decay curve came out.
Yeah.
You showed it. I mean, there's this curve from Steve Lamoureux's group. That was still the best limit there. You'd be
I think-
really close.
I think one of these,
That yellow one's from Steve Lamoureux.
yeah, that one, I think oh no, it's not that one. It's this little one here. Maybe it's shown on this, on our actual limit plot. But at one point, like we cross. Yes, so in this little triangle here.
You're better than Edwash.
Yeah. Okay, right, so
He is Edwash. Oh, no,
No,
that's Andy. I'm sorry, that's
yeah,
Andy.
so we're better than,
You're definitely better than Edwash, and you're even better than Andy.
yeah, and we're just like, I don't know.
Touching Steve. It's hard to beat Steve. Steve is.
Yeah.
Oh, that's the Casimir, man.
Yeah, that was the Casimir measurement that then Alex Ushkov turned into one of the tests.
Well, this one is not the Casimir, I don't think.
Yeah, it's the same apparatus, but they repurposed it to do this.
Okay, yeah.
Because
Because at one
over
point,
there in the basement of SPL.
oh yeah,
Yeah.
okay. Because at one point they had they did essentially fit a Casimir model and kind of looked at the residuals and did a
Yeah.
limit from this.
Yeah.
But this is now just using, they essentially have I think I have a diagram they're set up here. But effectively they're shielding the Casimir with enough gold that they're not measuring anything at all. They're just measuring.
On the Deca curve.
On the
lowest-
Deca.
Yeah, on the lowest curve. Yeah.
Yeah.
The one above that is the.
Yeah, okay.
Yeah, but this one, Alex Ryder was always very skeptical of this because they're measuring, he claimed that, I don't know if the paper was as weak as he said, but they basically measure zero. They don't see it. You can't really calibrate the force.
Yeah, so I know, I think within our group, there was a lot of skepticism of this result, but in talking to people,
Yeah.
I think this kind of became a lore in the group and then people
Yeah.
didn't really remember why. And in talking to people, I had a lot of people saying something like, oh, they choose some model for the Casimir and then fit the residuals, but you don't know if the Casimir model is right and that affects your limit.
Yeah.
And so I went back and I went through this paper and I don't know, convinced myself it's actually not,
Yeah, it looks fine.
it looks okay. I mean,
Deca
that
is
is,
pretty careful from the understanding.
yeah, they did see a background and then they like identified it physically in their system and made it go away, which is about as good as you can do when you see a background, and then they measured nothing, so. Yeah, I think it's, I mean, the one criticism is that they use like one, their bandwidth is like narrow enough that they're seeing one harmonic. which, we always claim that we're never gonna be fooled because we have so many harmonics. We have a really distinct signal template, which is true, but if you measure no backgrounds, it doesn't really matter.
Could you do something like, so harmonics are very good, but other things like get mixed up at harmonics? Is there like some irrational spacing of the fingers that gives you an even more kind of complicated template, or like, is it you're basically like fine already with
So the problem, really the fundamental problem is that the thing that's sourcing the Yukawa interaction is also the thing that's sourcing the scattered light. And that's the difference between the fingers. So if we make the fingers, if we change the kind of the width of the fingers and make some, crazy pattern there, the scattered light is just gonna look different too. We think it's really just like, yeah, I don't know, as long as the thing sourcing our signal is the same thing sourcing our background, it's hard to get around it with something like that.
Although, going faster, it's a good point, right?
Yeah.
It's gonna actually give you a distinct signature that get that mechanical susceptibility shown.
Yeah.
Or slow, you run your trucks really stiff, which is probably nice, but our trucks are at 30 hertz.
Oh, yeah,
Yeah. Makes it easier to go up on resonance.
right.
But we just have super low focus beams. So unfortunately, I have to go teach.
Okay.
So I don't know if you want to chat for a few more minutes. Or...
Sure, yeah, I'll hang around here and then I can.
Other folks are around. Sadly, I'm in the lab till like 5.
Okay.
So maybe we should chat now and I can go over to class.
Okay.
If there's stuff to talk about.
Sure.
Yeah. But yeah, really good talk.
yeah, thank you. Good help.